Okay, so in this section we will focus on one of the most famous digital controller architectures, which is the digital PID controller. So we already discussed the analog PID. Okay, if we have controller GC of S, for example, so it takes, for example, the error signal and applies some control signal to the system. And we know from our previous lessons that the control signal has a proportional part and it has an integral part. Okay, and it also has a derivative part. So those are the three terms of the PID, and this is where the term PID comes from: proportional, integral, and derivative. And okay, we know how we can obtain the transfer function GC of S, so it's just simply going to be Kp, okay, plus Ki over S plus Kd times S. And this is what we call the structure of the controller, and we knew how to design those parameters and everything. But now we want to obtain a discrete representation of this PID controller. So we want to extract the digital PID controller. So how do we do that? Okay, so we know that the GC of S, as I said, is just Kp plus Ki over S plus Kd times S. So one way of obtaining the discrete time version is just to use bilinear transformation, for example. So if we just replace the S by its bilinear transform expression, okay, which we already derived in previous lectures, we get a digital PID controller. Okay, so it's 2 over t, 1 minus Z inverse divided by 1 plus Z inverse. Okay, so this is one structure, one possible structure for the digital PID. Okay, let's keep it clear here. When we are talking about the digital PID controller, okay, there is we don't have only one structure. I mean, we can have many different structures because the digital is some approximation of the analog. So we can have different structures. It doesn't have to be only one structure. So for example, I mean, here we chose this particular structure in which we replaced the S term, for example, by its bilinear equivalent, which is equivalent to the trapezoidal integration, as we mentioned before. You can also have another structure. I mean, you can, for example, you can keep this integral term as is, and for the derivative term, you can say, okay, for this term, I will say it's going to be plus Kd times 1 minus Z inverse over T. Okay, so where does this come from? This comes from just the basic first order differentiation. So if you obtain the difference equation here, you'll just find that it's going to be E of k minus 1 divided by t, and then multiplied by Kd. So this is just the first order differentiation. So you can either use the bilinear transform, or for example, you can approximate the derivative by the first order differentiation and keep this one as is. Another option is also that you might use a rectangular integration instead of the trapezoidal integration. So for example, we know that from the trapezoidal integration we were approximating the integration in the form of a set of trapezoids, which is quite accurate, but it's maybe it makes things a little more complicated. So maybe one easier way to do the integration is to just use rectangular integration. And if you use rectangular integration, then where your transfer function will be t divided by 1 over Z inverse. Okay, I will leave this as an exercise, so you can easily derive this transfer function for rectangular integral. So, and then of course you multiply by the ki. I mean, so there is really a lot of flexibility here. I mean, you can use this transfer function. This is one option, or you can replace the derivative with this part. So that's another option. You can also replace the integral with this one. So that's a third option. You can use those two together. That's a fourth option. So you really have so many like different design for the digital PID controller. So all of these are different structures. All of those are different structures for the digital PID, and they are all valid. I mean, it's a matter of how simple you want your design to be, and how you want to proceed in this direction. So if we consider the most simplest of those forms, so the one that is basically using the rectangular integration and first order differentiation, so you will find that the transfer function is going to be something like this. So it's going to be kp plus ki times t divided by 1 minus z inverse, and then plus kd multiplied by or kd over t multiplied by 1 minus z inverse. And since we are anyway talking about a different controller, so we can just consider that our new ki is this one and our new kd is this term. So just to simplify things further, so it's anyway a different controller than the continuous time, so we don't need to stick to the older ki. So we can just call this ki times t our new ki. And yeah, here we are. So here we have one of the very famous structures for that digital PID controller. Okay, this is a digital PID controller, and yeah, and this is what you find in many of the, for example, in the industry, you find that when you see in the industry that someone is talking about PID and this PID is implemented on a microcontroller, then he is probably talking about the digital PID. He's not talking about the analog PID, and this is one of the most famous structures of the digital PID because it's quite simple. But as I said, you don't have to use this one. This is not the only structure that you can use. You can use other structures. Okay, so now we have talked about the aspect of the structure of the controller. The next part we're going to discuss the implementation part. So how do we realize this transfer function in hardware or in software? Okay, so if you want to implement this as a hardware logic function, for example, digital design, or want to implement it as a software, so how can we realize this? So this is the next thing that we move on.